Out of all the possible limit results, by far the most interesting is the 0 over 0. You may wonder, how is this allowed? How can you have 0 in the denominator? And the answer to that is, this is a limit. The denominator is approaching 0. It's not actually reaching 0. The denominator will be a small number close to 0. It can be a small positive number to the right side of 0 on the number line, or a small negative number to the left side of 0 on a number line. It will be close to 0, but it won't actually equal to 0. The same holds true for the numerator in a 0 over 0. It is a small positive or negative number. So 0 over 0 in a limit can also be written as a positive or negative small number over a positive or negative small number. Now here's the thing with these small numbers. They can end up in any proportion relative to each other. They can be equal size and cancel to be a 1, or the numerator could be, say, twice as large as the denominator and cancel to be a 2, or maybe 10 times as large, cancel to be a 10, or maybe 1,000,000 times as large, cancel to be 1,000,000, or many, many, many times as large and cancel to be a very large number. Just the same, the denominator might be twice as big as the numerator, and they will cancel to be a 1 over 2, or 0.5, or maybe 10 times as big, they'll cancel to be a 1 over 10, or 0.1, or maybe it'll be 1,000,000 times as big, and they'll cancel to be 1 over 1,000,000, or 0.000001, or many, many, many times as big, and it'll cancel to be a really small result. Couple that together with the fact that you have a positive or negative in the numerator or denominator, then a combination of signs can give you a positive or negative number. It means that you can result in any size number, and it can be positive, it can be negative, it can even be 0. Therefore, this is called indeterminate. It must be reworked to be able to determine the actual result, and that result can be any real number between negative infinity and positive infinity. And it can even be DNE, or does not exist. The method by which to rework it depends on the type. There are 5 main types to rework the 0 over 0 result, and I'm going to cover each of those here. The first one will be the power function. Power functions are characterized by x raised to a power, and that will exist in the numerator or denominator, or both, in one or more terms. The method by which to rework this is the factor and cancel method. Let's give an example. Say we have limit as x approaches 1 of x squared minus 1 over x minus 1. If I plug a 1 in, you have 1 squared minus 1 in the numerator and 1 minus 1 in the denominator. The numerator will be 1 minus 1, which is a 0. The denominator will be 1 minus 1, which is also a 0. We certainly have 0 over 0 here. We will now try to factor them, being that these are power functions. X is raised to a power. The numerator factors as a difference of squares. It will factor into an x plus 1 and an x minus 1. The denominator does not factor. It will remain as an x minus 1. If we retry the 1, we're still going to have 0 over 0, and you'll continue to have that until you cancel the factors that are making the 0. And that turns out to be the x minus 1 here. If you plug 1 into those, that's what is creating the 0 in the numerator and the denominator. Remember, that's its limit value of 0. It's just approaching that. Its actual value is a small number, but they're the same size, they're the same expression, and they therefore can be canceled, and that's our step, is to cancel after the factor. And so I cancel those out, and we're left with just an x plus 1. We no longer have 0 over 0. The 1 can plug in. We have 1 plus 1, which is a 2. Another type that we may encounter is the root combination. A root combination is characterized by a root involving x in some way, added or subtracted together with at least one other term. The method by which to rework the root combination will be the root conjugate. Let's look at an example. Limit as x goes to 36 of 6 minus root x over x minus 36. If I plug the 36 in for x, the square root of 36 is a 6, so the numerator will be 6 minus 6, that's a 0. The denominator will be 36 minus 36, that's also a 0. I do end up with 0 over 0. Now, since I have a root combination, it's in the numerator for this one. It is a 6 minus a root x, a root involving x combined by addition or subtraction to at least one other term. I can try the root conjugate method. I'm going to rewrite that limit as is, and I'm going to prepare it to multiply the numerator and denominator by the root conjugate. Now the root conjugate, you look at the root combination, 6 minus root x, and you're going to have as the conjugate the same expression with the opposite sign between the terms. 6 plus root x will be the root conjugate here. And we're going to multiply the numerator and denominator by that root conjugate so that we have a form of 1, and we're not changing the value, we're just changing the look. Now what we do is FOIL out the root conjugate pair, and important, do not FOIL out the non-root conjugate pair. We have the root conjugate pair in the numerator here. We're going to FOIL that out. The denominator, those are not root conjugates of each other, and you actually are going to not FOIL, you're going to leave those factored as is. So let's start the FOILing of the root conjugate pair in the numerator. 6 times 6, that's a 36. 6 times root x, that's a positive 6 root x. Negative root x times 6, that's a negative 6 root x. Negative root x times root x, that's a negative x. All this is over the denominator, which I'm going to leave alone. Another thing about conjugates is the outside and inside terms will actually be same value but opposite sign, and they will always cancel. Notice we have a plus 6 root x for the outside and a minus 6 root x for the inside, and those cancel each other out. And I'm going to do that for my next step, and I'm going to have then 36 minus x over x minus 36 times 6 plus root x. We have 0 over 0. We haven't changed that yet. However, it's starting to turn more into a power function type. Now, if the root had a fraction under it, it might turn into a fraction type, which is going to be handled in the number 3 type that I will be working with here soon. But this one turned into a power function, and so just like power functions up above, we're going to try factor cancel. These can't cancel just yet. 36 minus x and x minus 36, those are opposite signs of each other. So what I need to do is factor a negative out of one of them, either the numerator one or the denominator one, it doesn't matter which. I'm going to select the numerator just because there's less stuff up there. I'm going to factor the negative out. That changes the sign of each of the terms. So it will be a positive x and a negative 36 in the numerator. And now the x minus 36 are going to be a small number that are equal and can cancel each other out. We will go through the step of canceling them. We now have negative 1 over 6 plus root x. If I put the 36 in there for the x, the root of 36 is a 6. I have a negative 1 over 6 plus 6, and I'm going to end up with a negative 1/12. Another type you may encounter is the fraction function. That will have a fraction involving x in some way, combined together with one or more terms. The method by which to rework this will be the common denominator. Let's look at an example. Limit is x goes to 7 of 1 over 7 minus 1 over x minus 7. If I plug the 7 in for x, I'm going to have 1 over 7 minus 1 over 7. That's a 0. Over 7 minus 7, that's also a 0. So I do have the 0 over 0 indeterminate form happen here. Because I have fractions involving x, 1 over x, I'm going to look for a common denominator. Now what I have is a 1 over 7 and a 1 over x. The common denominator of 7 and x is 7 times x. So I'm going to multiply the first term by x over x and the second term by 7 over 7. That'll give me this result. Limit as x goes to 7. 1 over 7 times x over x minus 1 over x times 7 over 7. All of that over x minus 7. I'm going to multiply the 1 over 7 times x over x. That's going to be x over 7x. You just multiply the numerators and denominators with each other. And likewise, I'm going to multiply the 1 over x with the 7 over 7. That'll give me a 7 over 7x. They now have a common denominator, so they can be combined together over that common denominator. In this case, it's a subtraction, so it'll be x minus 7 over the common denominator of 7x. Now down in the overall denominator, I have an x minus 7 that I haven't worked with yet since it wasn't a fraction involving x. I'm going to put it over a 1, and the reason for that is once you have the fraction function type, part of the method after you have produced the common denominator is to reciprocate and multiply the overall denominator fraction with the numerator fraction. So we're going to reciprocate that denominator and multiply it with the numerator. The reciprocal will become 1 over x minus 7. We're going to multiply that with the numerator fraction, which was x minus 7 over 7x. We can now multiply fractions, multiply the numerators. X minus 7 times 1 is x minus 7. Multiply the denominators, which is 7x times x minus 7. It's still 0 over 0. It's been 0 over 0 this whole time, and it will continue to be 0 over 0 until you cancel the terms that are making the zeros, and that would be the x minus 7 in the numerator and denominator. This is turned into a power function type. We can cancel those out. So I will. That's leaving us a 1 in the numerator. I then have a 1 over 7x. The 7 can plug in, and I have a 1 over 49. Another type that you may encounter is the trig and power. This will involve a trig function. It can be any of the 6 trig functions: sine, cosine, cosecant, secant, tangent, and cotangent, together with power functions, x raised to a power. The method by which to work this out involves this identity. Limit as theta goes to 0 of sine of theta over theta equals 1. This is an identity that's derived later in calculus, but is just taken to be known here and is utilized to work out this type. One of the important things to be aware of here and to watch out for, you have sine of theta over theta. It's really important that those thetas match each other. Now the theta inside the sine, that's called its phase. That cannot be changed. But the one that it's paired off with, in this case in the denominator of this identity, has to match it. And that one can be changed using algebra. You have to make those be the same for this limit to equal 1. They have to be exactly the same. And that's part of the method to work this out. Another thing, cosine of 0 equals to 1, so cosines are never a problem with the trig and power type because cosine of 0 doesn't produce the 0 over 0 result. It gives you a 1 and has no influence. And therefore, it isn't involved in this identity, and it's not anything you need to worry about. Now, the other 4 trig functions, that would be the cosecant, the secant, the tangent, the cotangent, those you want to turn into sines and cosines. And we take each of the sines and we try to pair them off so that they have this form of sine of theta over theta, or theta over the sine of theta. It can also be the reciprocal of this. The reciprocal of this, if you have theta over sine of theta, would be the reciprocal of 1 over 1. It would still give you a 1. So those can be flipped around, and it's still the same result. So it's okay if the sine's in the denominator. The important thing is to pair off the thetas with each other. Let's look at an example. Say we have limit as x goes to 0 of sine of 9x over x cosine of 2x. If I plug in the 0, I have sine of 0 in the numerator. That's a 0. I have 0 times the cosine of 0. The cosine of 0 is a 1. 0 times 1 is a 0. And I do have the 0 over 0 indeterminate form here. Now, I'm going to make use of that identity. And as I mentioned, it's the sine functions that you're going to be making and pairing off to become the identity. So I need to separate that sine of 9x away from that x cosine 2x. And I'm going to do that like so. I'm going to move them apart. They're multiplying each other. The sine is in the numerator. The x cosine is in the denominator. So I'm going to keep them where they're at. You don't want to accidentally move them around here. Sine of 9x in the numerator, x cosine 2x in the denominator in separate terms. Now here's why I did this. I need to match the phase of the sine function, which is a 9x. I need a 9x in the denominator to pair off with it. Now I'm going to put it in. Bam, I'm just going to put it in like that. And it's now paired off, and those are then in the exact form of that identity, and that limit will be equal to a 1. But you can't just put that 9x there and expect it to be the same. You've changed it by putting it in there. So to compensate, we'll put 1 in the numerator. Let's put it above the other fraction. We'll put a 9x there. If you multiply those back, those 9x's will cancel out, and it will go back to the original. So we've just introduced them specifically to make that first fraction have a limit of 1. Now that second fraction, we're going to need to work with that a little bit more because there's now an x in the numerator and denominator. Those can cancel, so let's go ahead and cancel those out. And that's getting rid of the 0 over 0 problem with that one. The first fraction's a 0 over 0 for sure, but it has the exact form of the identity, and it will equal to a 1 in that ratio. So what we have in this situation is the first fraction will be a 1. And the second fraction will be 9 over cosine of 0. Well, cosine of 0 is a 1, so we have 1 times 9 over 1, and the result is a 9. Now, the last type you may encounter is the trig combination. The trig combination will be kind of similar to the root combination up above. It will be a trig function involving x, and it will be added or subtracted together with at least one other term. The method by which to rework this will be the trig conjugate. So it'll have some similarities to the root combination root conjugate that we saw up in number 2. Let's give an example. Let's say we have limit as x goes to 0 of 1 minus cosine x over sine x. If I plug in 0 for x, I will have 1 minus the cosine of 0. Well, the cosine of 0 equals to 1, so we have 1 minus 1. That's a 0. And in the denominator, we have sine of 0. Sine of 0 is 0, so we have 0 over 0. It is indeterminate. We then need to rework it. And we're going to rework it by the trig conjugate. Now, the trig conjugate, I'm going to get this ready to multiply. It will be similar to the root conjugate. We will take the trig combination, which is 1 minus cosine x, and write the same expression with opposite sign between the terms. So 1 plus cosine x, again multiply the numerator and denominator by that so that it's a form of 1, so we don't change the value, we just change the look. And just like the root conjugate up above, we're going to FOIL out the conjugate pair. That will be the 1 minus cosine x and the 1 plus cosine x, and we're not going to FOIL out the non-conjugate pair. So let's do that here. The first is 1 times 1, that's a 1. The outside is 1 times cosine x, that's a positive cosine x. The inside is negative cosine x times 1, that's a negative cosine x. And last is negative cosine x times cosine x, that's a negative cosine squared x. The denominator we're going to leave alone since that's a non-conjugate pair. We don't want to distribute or FOIL that out in any way. Just like the root conjugate result, the outside and inside terms are the same value but opposite signs, so they will cancel with each other, leaving us 1 minus cosine squared x. At this point, you will have some sort of Pythagorean trig identity. The one we'll want in particular is the sine squared of x plus cosine squared of x equals to 1, or rearranged, sine squared of x equals 1 minus cosine squared of x. If you look in our numerator, we have 1 minus cosine squared of x. That, from the Pythagorean trig identity, is equal to sine squared of x. And I'm going to replace it with then sine squared of x. We still have 0 over 0. We haven't changed that just yet. You don't change it until you cancel what's making the zeros. Notice that was the case for number 1, number 2, number 3, and number 5. They all are going to involve canceling out what is making the 0 in the numerator and denominator. Number 4 is a little different. That one you're making use of that identity, so you don't look for cancellation. But here you will. We're going to cancel one of the signs out. That actually leaves one of them in the numerator. Since it was a sine squared up there, there's one sign left over. But at this point, we no longer have 0 over 0. If we plug in the 0, we have sine of 0 in the numerator, which is 0. We have it over 1 plus cosine of 0. Now, cosine of 0 is a 1, so we're going to have 0 over 1 plus 1, 0 over 2. 0 divided by any non-zero number is always equal to 0. And therefore, we have 0 over 2 or 0 for this. Now, one last thing. If you look at all of the results I had come up with for each of the limits in 1, 2, 3, 4, and 5, you'll notice that they ended up being a wide, different set of possibilities. Each one was 0 over 0 indeterminate to begin with, but in the end, for number 1, we had 2. For number 2, we had negative 1/12. For number 3, we had 1 over 49. For number 4, we had a 9. And for number 5, we end up with a 0. So you can see how it can end up being a negative number, a positive number. It can even be 0. And that's why these always start out as indeterminate, and you have to go through and rework the problem to determine the result. How you rework it, it's these methods according to the form that the original function had. That is how you go and figure out the 0 over 0 indeterminate form.